Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the quantum roots of reality, into a world so small, so subtle, that it quietly shapes everything you see, everything you touch, and even the thoughts drifting gently through your mind right now. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the hidden structure of reality together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. It might be tempting to imagine that science begins with equations, with symbols written across chalkboards, or numbers carefully measured in laboratories. But in truth, many of the deepest questions begin somewhere much simpler. They begin with noticing. Long before anyone spoke of atoms or particles, people noticed patterns. A snowflake landing softly on a sleeve, intricate, delicate, and yet strangely familiar. No two are ever quite the same, and yet they all share something, a kind of quiet symmetry, a repeating structure, as if nature is gently following a hidden design. Over 400 years ago, a man named Johannes Kepler found himself walking across a bridge in Prague during a winter snowfall. He'd forgotten to bring a gift to a gathering, and as he searched for an idea, he noticed the snowflakes resting on his coat, each one different, and yet unmistakably similar. They all seemed to carry the same six-sided form, like a quiet whisper repeated again and again. And Kepler wondered, as anyone might in such a moment, why? Why should something so delicate, so fleeting, follow such a precise structure? He didn't have the tools we have today. No microscopes to peer into molecules, no quantum theory to describe the invisible. But he had curiosity, and that was enough to begin. He suspected that the answer lay not in the snowflake itself, but in something deeper, something hidden beneath what could be seen. Perhaps, he thought, the shape came from the way its smallest parts were arranged, from the building blocks of matter itself. And in that quiet realization, standing in the snow, Kepler found himself, as he later described, knocking on the door of chemistry. Today, we would say he was also knocking on the door of quantum physics, because now, centuries later, we understand that the shape of a snowflake is not random at all. It emerges from the way water molecules arrange themselves as they freeze, guided by invisible rules that govern how atoms connect, how electrons move, and how energy flows. Rules that belong to a deeper layer of reality, a layer we cannot see directly, but one that quietly determines the forms we observe. And once you begin to notice this, you start to see it everywhere. In the hexagonal patterns of a honeycomb, where bees construct their hives with remarkable efficiency. In the arrangement of seeds within a fruit, spiraling outward in precise repeating sequences. Even in the way crystals form, or the way light reflects and bends through the world around you. There is a sense, subtle but persistent, that nature is not simply chaotic, it is structured, ordered, almost as if it is following a set of rules written beneath the surface. For a long time, these patterns were simply observed, admired, and sometimes puzzled over. But as science slowly advanced, a question began to take shape. One that would eventually lead us into the quantum world. What are these patterns made of? What is the smallest piece of reality? that gives rise to everything else? At first, the answers were simple. Matter was thought to be made of tiny solid particles, little indivisible units called atoms. These atoms were imagined as miniature spheres, like grains of sand forming the fabric of the universe. But as experiments became more precise, and as curiosity pushed deeper, that picture began to dissolve. Atoms were not solid. They had structure, and within that structure something even stranger was waiting. Something that would challenge not only our understanding of matter, but our understanding of reality itself. Because when scientists began to look closely, very closely, at the behavior of these tiny building blocks, they found that they did not behave like ordinary objects at all. They didn't move in predictable paths. They did not settle into fixed positions. And in some sense, they did not even seem to exist in a single definite state. It was as if, at the smaller scales, reality itself became softer, less certain, more fluid, like a shape that has not yet decided what it wants to be. And yet, from this strange and uncertain foundation, everything you know emerges. The ground beneath your feet, the air you breathe, the stars scattered across the night sky, all of it, rising from a world that behaves in ways that feel almost dreamlike. So tonight, as we begin this journey, you might imagine yourself standing in that quiet snowfall again, watching those delicate shapes drift gently downward, each one carrying within it a hidden story, a story of particles and patterns, of invisible rules and quiet symmetries, a story that begins with something as simple as a snowflake, and leads us slowly and gently toward the deepest questions we can ask about reality. And as we continue, we'll begin to uncover how those hidden rules were first discovered, how a small crack appeared in our understanding of the world, and how that crack would eventually open into an entirely new way of seeing the universe. For now, just let the idea settle, that beneath everything familiar, there is a deeper layer, quiet, subtle, and waiting to be understood. If you stay with that image for a moment, a quiet snowfall, patterns forming without effort, it can begin to feel as though nature already knows what it is doing, as though the universe has always been this way, ordered, predictable, calm. And for a long time, scientists believed exactly that. By the end of the 19th century, physics seemed almost complete. The laws of motion were understood. Gravity had been described with remarkable precision. Light, electricity, and magnetism had been woven together into a single, elegant framework. It felt to many like the great puzzle of nature was nearly solved. There is a quiet confidence that comes with such a moment. Like standing in a room where every piece of furniture has been carefully arranged, everything in its place, nothing left uncertain. But sometimes it is in those very moments of certainty that the smallest inconsistency begins to whisper, not loudly, not dramatically, just enough to be noticed. One of those whispers came from something very simple, the glow of heated objects. If you've ever watched a piece of metal being heated, perhaps in a workshop, or even imagine the coils of a stove warming up, you may notice how its colour changes. First it glows a soft red, then orange, then a brighter yellow, and eventually, if hot enough, a pale white. This change in colour is not random. It reflects how the object emits light as it becomes hotter. And by the late 1800s, physicists believed they understood how this should work. They had equations, beautiful, logical equations, that predicted how much light should be emitted at each colour, at each temperature. But when they compared those predictions to actual experiments, something didn't quite fit. At certain colours, especially toward the higher energy end of the spectrum, the equation suggested something impossible. They predicted that a hot object should emit an infinite amount of energy, an endless glow, which of course does not happen. The real world remained calm and finite, while the equations spiraled into something unphysical. It was a small mismatch, a quiet disagreement between theory and reality. But it was enough. Because in science, even the smallest crack can widen if you follow it carefully. Around the year 1900, a physicist named Max Planck decided to take a different approach. He was not trying to revolutionize physics. In fact, he was trying to fix it, to gently adjust the equations so they would align with observation. And in doing so, he made a suggestion so subtle and yet so profound that it would quietly reshape our understanding of the universe. Planck proposed that energy is not emitted in a smooth, continuous flow, like water pouring from a stream. Instead, it comes in tiny, discrete packets, little bundles of energy, each one with a size that depends on the colour of the light. You might imagine it not as a steady glow, but as a soft rain of invisible droplets, each droplet carrying a specific amount of energy. And the deeper insight, the one that would echo through all of physics, was that the energy of each of these tiny packets depends on how rapidly the light vibrates. The faster the vibration, the more energetic the packet. The slower the vibration, the gentler the energy it carries. Planck introduced a new constant, a number that sets the scale of these energy packets, a kind of quiet conversion factor between vibration and energy. Today, we simply call it Planck's constant, but at the time, it was something entirely new, a number that did not emerge from classical physics, a number that seemed to belong to a deeper layer of reality. And yet, what is perhaps most remarkable is that Planck himself did not fully believe what he had discovered. To him, this idea of energy coming in discrete packets was a mathematical trick, a clever way to make the equations work. He did not imagine that light itself was actually made of these little bundles. He did not yet see that this small adjustment was pointing towards something far more radical. It's a quiet reminder that sometimes we can uncover truths that we are not yet ready to accept. That understanding often arrives slowly, even after discovery. For a few years, Planck's idea remained just that, a useful tool, a way to make sense of experimental data. But it lingered, like a faint echo in the background of physics. And then, in 1905, a young physicist named Albert Einstein took that idea and followed it a little further. He looked at a different phenomenon, one that also seemed simple at first glance. When light shines on a metal surface, it can cause tiny particles, electrons, to be released. You might imagine that if you shine brighter light, you would release more electrons, more light, more energy, a straightforward relationship. But experiments showed something unexpected. If the light was too gentle, too low in its vibration, then no electrons were released at all. No matter how bright the light became, you could shine it endlessly and nothing would happen. But if you increase the vibration just enough, even a faint light could suddenly knock electrons free. It was as if the brightness didn't matter as much as the quality of the light itself. Einstein realized that this only made sense if light truly behaved as Planck had suggested, not as a continuous wave, but as a stream of tiny packets, each packet carrying a specific amount of energy. If a single packet did not carry enough energy, then no electron would be released, no matter how many packets arrived. But if even one packet carried enough energy, it could do the job. And in that moment, something shifted. Light was no longer just a wave spreading smoothly through space. It became something more tangible, something that arrived in little bursts, almost like tiny messengers, each one delivering a precise amount of energy. This idea was deeply unsettling at the time, Even Planck himself was hesitant to accept it, but it worked. It explained the experiments, and more importantly, it opened a door into a world where energy is not continuous, where the smallest scales are not smooth, and where the familiar rules of everyday experience begin to fade. If you listen closely, you can almost feel it, the gentle breaking of an old idea, the quiet realization that reality, at its deepest level, might not be as continuous as it seems, that beneath the smooth surfaces of the world, there may be a kind of subtle granularity, not harsh or abrupt, but softly divided into pieces, like light falling in droplets, or like time itself, ticking quietly, one moment at a time. And as we continue, we'll begin to explore what happens when this idea is taken seriously, what it means for something to exist not in a single definite state, but in many possibilities at once, and how, from that strange and delicate foundation, the entire universe continues to unfold. If you let that idea rest gently for a moment, light falling not as a continuous stream, but as tiny discrete packets, it begins to change something subtle in how you imagine the world, not dramatically, just enough to make things feel slightly less solid than before. For centuries, light had been one of the most familiar things in nature. It illuminated the world, revealed shapes, cast shadows. It was something you experienced every day without question, and by the late 19th century, it was widely understood as a wave, something that spread smoothly through space like ripples across the surface of water. That picture worked beautifully. It explained colours, reflections, interference patterns, even the soft blending of light and shadow that fills a room at sunset. And yet, with Planck's quiet suggestion and Einstein's careful step forward, that picture began to soften. Because now, light was no longer just a wave, it was also something else, something more tangible. Imagine for a moment standing in a dimly lit room. A small beam of light passes through a window, catching tiny particles of dust suspended in the air. You might notice how those particles seem to sparkle, each one briefly illuminated as it drifts through the beam. Now imagine that instead of a continuous glow, that light is made of countless tiny arrivals, each one a small, precise delivery of energy. Not a smooth flow, but a quiet sequence of gentle impacts. This is the idea that began to take shape in the early 20th century. Light in certain situations behaves as if it is made of individual pieces. We now call these pieces photons, though the name itself came later. At first, this was difficult to accept, even for the scientists who were discovering it. There was something deeply unsettling about the idea that light could be both a wave and a collection of particles. It didn't fit neatly into any existing category. It was as if nature had quietly refused to choose. But the evidence continued to grow. Experiments like the photoelectric effect showed that light interacted with matter in ways that only made sense if it arrived in these tiny packets, each one carrying a specific amount of energy, determined not by how bright the light was, but by how rapidly it oscillated. You might think of it this way. Imagine rain falling onto a surface. If the raindrops are too small and gentle, they might not disturb the surface at all. You could have countless tiny droplets landing softly and nothing would change. But if a single drop is large enough, even just one, it can create a visible ripple. In the same way, light with a low level of energy per packet might arrive in large amounts, but still fail to produce an effect, while light with higher energy per packet, even if faint, can suddenly cause something to happen. And so, brightness alone is not enough. What matters is the energy carried by each individual drop of light. This realization marked a quiet turning point. because it suggested that the world at its smallest scales does not behave in smooth, continuous ways. Instead, it moves in steps, not harsh steps, not abrupt or mechanical, but gentle, indivisible units, little quanta. And once you begin to see the world this way, it becomes difficult to return to the older picture. Light is no longer just a wave flowing through space. It is also something that arrives, something that interacts, something that can, in a sense, be counted. And yet this is where things become even more subtle. Because while light behaves like particles in some situations, it still behaves like a wave in others. It can spread out, it can interfere with itself, it can create patterns that only make sense if it is extended across space. So what is it really? A wave? A particle? Something in between? Or something beyond both? At this point, early physicists found themselves in unfamiliar territory. The language they had used for centuries, words like object and trajectory, wave and particle, began to lose their clarity. They were trying to describe something that did not quite fit into the categories they had. And so, rather than forcing the world to match their expectations, they began to adjust their expectations instead. They allowed for the possibility that reality, at its deepest level, might not be easily pictured, that it might require a new kind of thinking, a softer way of holding ideas, less rigid, more open and more open. As this shift unfolded, something remarkable happened. The study of light began to merge with the study of matter, because if light could behave like particles, then perhaps particles could behave like waves, and if both were true, then the distinction between them might not be fundamental at all. It might simply be a reflection of how we choose to observe them. This idea would soon lead to one of the most important experiments in all of physics, an experiment so simple in its design, and yet so profound in its implications, that it continues to shape how we understand reality to this day. But before we arrive there, it's worth pausing for just a moment to let this gentle shift settle in. That something as familiar as light, something that fills every day of your life, is not quite what it seems. That beneath its soft glow, there is a structure, a rhythm, a quiet discreteness, and perhaps more importantly, that our understanding of the world is not fixed. It evolves, it adapts, it deepens, one small insight at a time, and sometimes those insights arrive not as dramatic revelations, but as quiet adjustments, a slight change in perspective, a new way of seeing something that was always there, like noticing the pattern in a snowflake, or the glow of heated metal, or the way a beam of light catches dust in the air, revealing just for a moment that even the most ordinary things carry within them a deeper story. And as we continue, that story will become stranger and more beautiful, because soon we will encounter a simple experiment where even a single particle seems to explore more than one path at once, and in that moment, the idea of a single, definite reality will begin to soften even further. As you let those earlier ideas settle, light arriving in tiny packets, reality beginning to feel just slightly less continuous, something even more subtle starts to emerge, a quiet shift, not in what we see, but in how we understand what's there to be seen. For most of your life, and for most of human history, the world has appeared to follow a very simple rule. Things are what they are. A cup rests on a table. A door is either open or closed. A coin, when placed in your hand, is either heads or tails. Even if you do not know which side the coin is facing, you assume that it has already chosen. That the uncertainty exists only in your knowledge, not in the coin itself. This is the essence of what we might call a classical view of reality, the idea that everything has a definite state, whether or not you happen to be aware of it. It is a comforting idea, stable, predictable, like a quiet room where everything remains in place, even when you turn away. But as scientists began to explore the behavior of the smallest building blocks of matter, they found that this assumption did not always hold. In fact, at very small scales, it seemed to break down entirely. Imagine, for a moment, that same coin in your hand, but now, instead of being either heads or tails, it exists in a state that is somehow both at once, not flipping rapidly between the two, not hiding one side from you, but genuinely holding both possibilities together. You might picture it as a soft blur, a gentle overlap of two realities, and only when you look, only when you make a measurement, does it settle into one outcome, heads or tails. This idea is known as superposition, and while it may sound abstract, it reflects something very real about how nature behaves at its smallest scales. Particles like electrons, for example, have properties that can exist in multiple possible states at once, not because we lack information, but because the system itself has not yet chosen a single outcome. This is an important distinction, because in everyday life we often use probability to describe uncertainty. There might be a chance of rain tomorrow, a likelihood that a coin will land one way or another. But these probabilities reflect something about us, about what we do not know. In the quantum world, however, probability is different. It does not arise from ignorance. It arises from the nature of reality itself. The world at this level does not simply hide its details from us. It genuinely exists in a range of possibilities until something brings it into focus. And this can be difficult to accept at first, because it challenges something deeply intuitive, the idea that things are always definite, even when unobserved. Instead, we are asked to consider a world where definiteness is not fundamental, but emergent, where clarity comes later, not first. You might think of it like a photograph that has not yet developed. The image is there in some sense, but it has not yet resolved into something you can clearly see. Only when the process completes, only when the measurement occurs, does the picture become sharp. Before that, it exists in a kind of a gentle ambiguity, and yet, despite this uncertainty, the quantum world is not chaotic. It follows precise rules. The probabilities are not random guesses, but carefully structured patterns that can be calculated and predicted with extraordinary accuracy. There is a quiet order within the uncertainty, a kind of hidden rhythm, and over time physicists learn to work with this new kind of reality, not by forcing it into familiar categories, but by allowing it to be what it is. They began to describe systems not in terms of definite positions or paths, but in terms of possibilities, distributions, waves of potential. And when these possibilities are allowed to interact, something remarkable happens. They can combine, they can reinforce one another, or cancel each other out, much like overlapping ripples in water. And this is where the story begins to deepen, because if a particle can exist in multiple possibilities at once, then those possibilities can influence each other, even before anything is observed, even before anything is decided. It suggests that reality, at its most fundamental level, is not built from solid objects moving along fixed paths, but from a kind of unfolding landscape of potential, a landscape where what is emerges from what could be. And perhaps as you sit with that idea, it doesn't need to feel unsettling. It can simply feel softer, less rigid than we once imagined, more open, like a quiet space where possibilities rest gently, waiting to take form. And in that space, the familiar rules begin to loosen. Certainty gives way to probability. definiteness gives way to potential, and the world becomes something not fully fixed, but continuously forming. As we continue, we'll begin to see how this strange and delicate behaviour reveals itself in a single, elegant experiment. An experiment where even one tiny particle seems to move as if it were many at once, where paths overlap, interfere and reshape one shape. Another is before finally settling into a single quiet outcome. If the idea of a world that holds many possibilities at once feels gentle, almost abstract, there is a moment in physics where that idea becomes something you can almost see. Not directly, of course, but clearly enough to leave a lasting impression. It comes from an experiment that is, in its design, surprisingly simple. So simple, in fact, that it can be described in just a few steps. Imagine a quiet, darkened space. At one end, there is a device that releases tiny particles, electrons, for example, one at a time. At the other end, there is a screen that can detect where each particle arrives, marking its position with a small point of light. And between them, there is a barrier, a thin wall with two narrow openings cut into it, two slits. If you picture this setup, it might feel almost like a gentle game. Particles travelling forward, passing through one opening or the other, and then landing on the screen behind. Now, if these particles behaved like tiny solid objects, like grains of sand or small pellets, you would expect a very simple result. Some particles would pass through the left slit, others would pass through the right, and on the screen behind you would see two clusters forming, one behind each opening, a soft accumulation of dots, two gentle bands of arrival. That would be the classical expectation, clear, predictable, comforting. But when the experiment is performed, something very different appears. Instead of two bands, the screen begins to fill with a series of delicate stripes. Bright regions where many particles arrive, and darker regions where almost none do. A pattern of alternating light and shadow. And if you've ever seen waves, ripples spreading across water, overlapping and interacting, you might recognize this pattern, because it looks exactly like what waves produce. Where two sets of waves overlap, they can reinforce each other, creating peaks, or cancel each other out, creating calm, quiet spaces in between. And so, seeing this pattern, one might be tempted to say, these particles must be behaving like waves, and in a sense that is true, but the story does not end there. Because something even more subtle happens when we slow the experiment down. Instead of sending many particles at once, we release them one by one, gently, patiently, each particle travelling alone, passing through the slits, arriving at the screen. You might expect that, with only one particle at a time, the pattern would disappear. After all, how can a single particle create an interference pattern? How can it overlap with anything else if it is alone? And yet, if you wait long enough, if you allow many individual particles to arrive, one after another, the same pattern begins to emerge, slowly, quietly, dot by dot, stripe by stripe, as if each particle somehow knows about the pattern that is forming, even though it arrives alone. And this is where the experiment becomes truly profound, because it suggests something that feels almost impossible at first, that each particle does not simply pass through one slit or the other, like a tiny object choosing a path, but in some sense, explores both possibilities, as if it spreads out, like a wave, passing through both openings at once, and then, somehow, those possibilities interfere with each other, shaping the likelihood of where the particle will eventually be detected. It is important to say this gently, not as a rigid statement, but as a way of picturing something that resists simple description. Because in truth, We do not see the particle moving through both slits. We only see where it begins and where it ends. But the pattern it leaves behind tells a deeper story. A story in which the path is not fixed, in which the journey is not singular, in which the particle's behaviour reflects a kind of openness, willingness to explore more than one route. You might imagine it like a soft mist drifting through the slits, rather than a solid object passing cleanly through one side, or like a ripple that spreads outward, touching both openings at once, before gathering itself again on the other side, and yet when the particle is finally detected, it appears in one place, a single point, a definite outcome, as if all the possibilities that existed before have gently settled into one. This experiment has been repeated many times, with electrons, with light, even with larger particles, and each time the result remains the same. The pattern persists, the mystery remains. And perhaps the most intriguing part is this. If you try to observe which slit the particle passes through, if you place a detector at the openings to watch its path, the pattern disappears, the stripes fade, and what remains are the two simple bands you would expect from classical particles. It is as if the act of observing, of asking the question, changes the behaviour itself, and in that moment something becomes clear. Not in a sharp, defined way, but in a quiet, unfolding sense, that at the smallest scales, reality is not simply a collection of objects moving through space. It is something more delicate, more responsive, more intertwined with the act of observation than we might have imagined. And so, this simple experiment, with its quiet setup and its gentle pattern, becomes a doorway. A doorway into a world where paths are not singular, where outcomes are shaped by possibilities, and where the line between what is and what could be becomes softly blurred. As we continue, we'll begin to explore how this idea can be taken even further, how some physicists have come to describe particles not as choosing a path, but as somehow taking all possible paths at once, not in a chaotic way, but in a way that follows a deeper hidden logic, a logic that quietly governs how the universe unfolds, one possibility at a time. As that image lingers, the quiet pattern forming on the screen, each tiny point arriving as if guided by something unseen, a deeper question begins to emerge. If a single particle can create such a pattern, if it can behave as though it has passed through more than one opening, then what exactly is it doing between the moment it begins its journey and the moment it arrives? It is a simple question, and yet it leads us into one of the most subtle and beautiful ways of thinking about reality. There is a perspective introduced by the physicist Richard Feynman that offers a gentle way of imagining this process, not as a rigid answer, but as a kind of story, a way of picturing something that cannot be directly seen. Instead of asking which path the particle takes, Feynman suggested something different. What if it takes all of them, not one or the other, not switching between them, but, in a sense, exploring every possible route at once? You might pause there for a moment, not to analyse, but simply to let the idea settle. Imagine a particle leaving its source. Instead of following a single defined path, it spreads out into a soft cloud of possibility. Each possible route, straight ahead, slightly to the left, slightly to the right, even paths that wander in gentle curves, all of them are in some sense included. Not equally, not randomly, but all present. You might picture it like a drop of ink placed in still water. At first it is concentrated, a single point, but then, slowly, it begins to spread, soft tendrils reaching outward, exploring the space around it. The ink does not choose one direction, It flows into all directions at once, and yet, when it settles, it forms a pattern, not chaotic, but shaped, guided by the medium through which it moves. In a similar way, the quantum description of a particle suggests that every possible path contributes to the final outcome. Some paths reinforce each other, gently increasing the likelihood that the particle will arrive in certain places. Other paths cancel each other out, making some regions less likely, or even entirely empty. It is not that the particle physically travels each path in the way we might imagine a small object moving through space. It is that the structure of reality itself allows for all these possibilities to be considered and combined, and from that combination, a pattern emerges. If you were to describe it mathematically, it would involve assigning a kind of weight or influence to each possible path, and then combining them carefully to determine the overall outcome. But there is no need to follow the mathematics here. It is enough to hold on to the feeling that every possibility plays a role, that reality is not built from a single line, but from many overlapping threads. And where those threads align, something becomes more likely. Where they do not, something fades. This way of thinking is sometimes called the sum over paths approach, but rather than focusing on the name, it may be more helpful to imagine the process as a kind of quiet gathering. All the possible ways something could happen, gently contributing to what does happen, and this idea, while subtle, offers a kind of peace, because it suggests that the universe does not rush toward a single outcome. It allows for exploration, for possibility, for a kind of soft unfolding, even at the smallest scales, and yet when the journey ends, when the particle arrives, we still observe a single, definite result, one point on the screen, one outcome. It is as if all the possibilities that existed along the way have come together and resolved into a single moment, not abruptly, but naturally, like a wave settling into stillness, or a cloud of mist condensing into a single drop. There is something deeply elegant about this picture, because it bridges the gap between uncertainty and certainty, between possibility and reality. It allows both to exist without forcing one to replace the other, and perhaps, if you sit with it long enough, it begins to feel less strange, less like a contradiction, and more like a quiet extension of how things already are. After all, even in everyday life, we often consider many possibilities before something happens, paths we might take, choices we might make, outcomes that could unfold in different ways, and then, gradually, one path becomes real. The others fade into the background, not because they never existed, but because they were possibilities, not outcomes. In the quantum world, this idea is taken to its deepest level, not just in thought, but in the fabric of reality itself. And yet, there is still something unresolved. Because while this way of thinking tells us how to calculate what will happen, it does not fully explain what it means. Does the particle truly explore every path? Or is this simply a useful way of describing something beyond our current understanding? Are these possibilities real, or are they just part of the mathematical language we use to describe the world? These questions remain open, not as problems to be solved immediately, but as gentle reminders that our understanding is still evolving, that even with all we have discovered, there is still a layer of mystery, and perhaps that is not something to resist, but something to appreciate, because it leaves room for wonder, for quiet curiosity, for the sense that reality is deeper and more subtle than any single explanation can capture. As we continue, we will step even further into that mystery, into a place where not only paths, but particles themselves can become connected in ways that seem to transcend distance, where two separate things begin to behave as one, and where the idea of separation itself begins to soften. As you sit with that image, a particle quietly exploring many paths at once, possibilities weaving together before settling into a single outcome, there is a gentle realization that begins to take shape. We have learned how to describe this behavior. We can predict it. We can even build technologies that depend on it. And yet, we do not fully understand what it means. There is a quiet gap here, not in the mathematics, not in the results, but in the interpretation, in the story we tell ourselves about what is really happening. Because quantum mechanics in many ways is like a beautifully crafted set of instructions. It tells us with remarkable precision how to calculate the outcomes of experiments. If you prepare a system in a certain way, if you let it evolve, if you measure it at a particular moment, the theory will give you the probabilities of what you will observe, and it does so with extraordinary accuracy. Again and again, across countless experiments, the predictions match what is seen. There is no doubt that the theory works. And yet, it remains strangely silent on a deeper question. What is actually happening in between? When a particle exists in many possibilities at once, what does that mean for reality itself? Are those possibilities real? Do they coexist in some hidden way? Or are they simply part of the language we use, a tool for calculation rather than a description of what truly is? These questions form what is often called the interpretation problem of quantum mechanics. But rather than thinking of it as a problem to be solved, it may be gentler to see it as an open space, a place where different ways of understanding can quietly coexist. Some physicists take a very practical view. They say, in essence, the theory works and that is enough. It gives us the right answers. It allows us to build devices, to make predictions, to explore the world. Perhaps we don't need to ask what it means beyond that. Others feel that this is not quite satisfying. They wonder whether there is a deeper layer, a more complete picture, waiting to be uncovered. A way of understanding quantum behavior that restores a sense of clarity, of definiteness, even if it requires new ideas. And then there are those who embrace the ambiguity itself, who suggest that reality may not have a single, fixed description beneath the surface, that the act of observation, of interaction, plays a fundamental role in shaping what becomes real. You might imagine it like a quiet conversation between the observer and the world, not a forceful interaction, but a gentle meeting, where what is possible becomes what is actual. Before that moment, things remain open, not undefined in a chaotic way, but softly unformed, like a thought that has not yet been spoken, or a shape that has not yet settled into place. This idea can feel unfamiliar, because in everyday life, we're used to a world that exists independently of our attention. The chair remains where it is, whether we look at it or not. The sky continues its quiet motion, regardless of whether we notice it. But at the smallest scales, the distinction between what is and what is observed becomes less clear. Not because reality depends on us in a personal sense, but because the act of interaction, of measurement, cannot be separated from the system itself. To observe something is not simply to watch it from a distance, it is to become part of the process, and in doing so, to influence the outcome. This does not mean that reality is subjective. It does not mean that things only exist when we think about them. Rather, it suggests something more subtle, that the properties of a system, the things we can say about it, are not fully determined until they are brought into interaction with something else, until they are, in a sense, asked. And this brings us back in a quiet way to the experiment we explored earlier, the particle passing through two slits, forming a pattern when left unobserved. but behaving differently when we attempt to track its path. It is not that the particle changes its mind, it is that the conditions of the experiment, the nature of the interaction, shape what becomes possible. And so we are left with a picture of reality that is both precise and open, structured and yet not fully fixed, a world in which possibilities exist in a kind of gentle suspension until they are drawn into form. And perhaps as you rest with this idea, it does not need to feel unsettling. It can feel spacious, like a quiet landscape at dawn, where shapes are present, but not yet sharply defined, where the world is there, but still unfolding. There is something calming in that, a reminder that not everything needs to be resolved immediately, that some questions can remain open without losing their meaning. And in the case of quantum mechanics, that openness has not prevented progress. In fact, it has accompanied some of the most profound advances in science, because even without a final interpretation, we have learned how to work with these ideas, to harness them, to build new forms of technology, to explore connections that were once thought impossible. And as we move forward, we will begin to encounter one of those connections, a phenomenon where two particles, separated by distance, begin to behave as though they are part of a single, unified system, not bound by space in the way we might expect, not independent in the way we are used to imagining, but quietly linked in a way that challenges our sense of separation. And in that connection, the story of quantum reality will deepen once more. As those ideas settle gently, a world of possibilities, of paths that overlap, of outcomes that form only when something is observed. There is another quiet discovery waiting just beyond, a discovery that feels at first even more surprising because it does not simply question certainty, it questions separation. In everyday life, distance feels meaningful. If two objects are far apart, we assume they are independent. What happens to one does not immediately affect the other. A coin on your table does not influence another coin on a distant shore. This sense of separation is so natural, so deeply woven into how we experience the world that we rarely question it. But at the quantum level, this assumption begins to soften. Imagine for a moment that you prepare two particles together in a very particular way, not just placing them side by side, but allowing them to become part of a single, shared system. You might picture it like two notes played together in a chord, no longer separate sounds, but part of one combined harmony. Once prepared in this way, the particles are said to be entangled. It is a quiet word, but it carries a profound meaning, because entanglement suggests that even when the particles move far apart, even when they drift to opposite ends of space, they are still, in some sense, connected, not by a visible thread, not by a signal travelling back and forth, but by something deeper, something built into their shared origin. To see what this means, it helps to return to a simple image. Imagine two coins, but not ordinary coins. These are special in a very subtle way. They are prepared so that whenever one is found to be heads, the other is always tails, and whenever one is tails, the other is heads. At first, this may not seem too unusual. You might think that each coin simply decides its state in advance. One is heads, the other tails, and we just do not know which is which until we look. But in the quantum world, something different is happening. Before you look, before any measurement is made, neither coin has chosen. They exist together in a shared state of possibility, not one fixed arrangement, but a combination of both. And yet, when you observe one of them, when you gently ask it for its state, it gives you a definite answer, heads perhaps. And in that same moment, the other coin, no matter how far away it may be, is found to be tails. instantly, not after a delay, not through a signal travelling between them. But as part of the same unfolding event, it is as though the two outcomes are not separate at all, but two aspects of a single, shared reality. And this is what makes entanglement so intriguing. It does not allow us to send messages faster than light. It does not break the broader structure of physics, but it does suggest that the way we think about separation, about independent objects existing in distant places, may not be fundamental. Instead, what appears to be separate may be part of a deeper whole, a system that extends across space, even when its parts are far apart. Einstein himself found this deeply unsettling. He referred to it somewhat famously as spooky action at a distance, not because it was mystical, but because it seemed to challenge the idea that physical influences should travel through space in a continuous way. And yet, over time, experiments have confirmed that this behaviour is real. Again and again, measurements have shown that entangled particles exhibit correlations that cannot be explained by any simple, hidden arrangement. No pre-assigned values waiting to be revealed. Instead, the outcomes seem to arise in the moment of observation, consistent with the shared structure of the system as a whole. You might imagine it like two dancers performing a perfectly synchronized movement, even when they cannot see each other, not because they are communicating in real time, but because they are following the same underlying choreography. And in the quantum world, that choreography is written into the state of the system itself. There is something quietly beautiful about this, because it suggests that connection does not always depend on proximity, that things can be linked, not by distance, but by relationship, by the way they were formed, by the structure they share. And while this behaviour is most clearly seen at very small scales, it carries a deeper message, a reminder that the divisions we perceive between here and there, between one object and another, may not be as absolute as they appear, that beneath the surface and there may be a kind of unity, subtle, hidden, but real. As we continue, we will begin to explore how this idea of connection, this shared structure across space, becomes more than just a curiosity, how it forms the foundation of a new way of thinking about information itself, a way that does not rely on simple ones and zeros, but on a richer, more fluid description of possibility. And in that shift, we will begin to see how the strange behaviour of quantum systems can be harnessed, not just to understand the universe, but to shape the technologies of the future. As a sense of connection lingers, two distant particles moving as if they share a quiet understanding, another idea begins to emerge, not about matter, not about motion, but about something even more subtle: information. In everyday life, information feels simple: a message written on a page, a number stored in a device, a light that is either on or off. At its most basic level, information in our modern world is built from clear choices: yes or no, 1 or 0, on or off, like a switch. Everything in a classical computer, every image, every sound, every piece of text is ultimately broken down into these simple units, bits, tiny decisions, each one holding a definite state. And just like the classical world we explored earlier, each bit is assumed to be one thing or the other, even if we do not yet know which. But when we step into the quantum world, that simplicity begins to soften. Because here, the smallest unit of information does not behave like a fixed switch. It behaves more like the coin we imagined earlier. A coin that is not simply heads or tails, but can exist in a gentle combination of both. This is what we call a qubit, a quantum bit. And rather than thinking of it as a switch, it may be more helpful to imagine it as something like a dimmer light, not just fully off or fully on, but capable of holding a range of possibilities in between. a soft glow, a mixture, a balance that can shift and change. But even this is only part of the story, because a single qubit on its own already carries more richness than a classical bit. It holds a blend of possibilities, a kind of layered state that cannot be captured by a simple yes or no. And when you bring multiple qubits together, something remarkable begins to happen. They can become entangled, just as we saw with particles earlier. And when that happens, their states no longer independent. They form a shared system, one that must be described as a whole. You might imagine it like a group of musicians playing together in harmony. Each instrument contributes its own sound, but the music itself cannot be reduced to any single part. It is the combination that matters, the relationship between them. And in the quantum world, these relationships can become incredibly rich. Not just a few possibilities, but many. An entire landscape of potential configurations, all existing together in a delicate balance. And this is where the idea of quantum information begins to reveal its power. Because instead of processing one possibility at a time, as classical systems do, a quantum system can, in a sense, hold many possibilities at once, not by rushing through them, not by switching rapidly between them, but by allowing them to coexist. You might picture it like exploring a vast landscape. A classical system walks one path at a time, step by step, slowly moving from one place to another. But a quantum system, in a soft and abstract way, can spread out across the landscape, touching many paths simultaneously, feeling the shape of the terrain all at once, and then, when the process is complete, it gathers that information into a single outcome, a result shaped by all those overlapping possibilities. This is what gives quantum computing its potential, not speed in the usual sense, but depth, a richness of structure, an ability to work with a space of possibilities that grows far beyond what classical systems can easily handle. And yet, as with everything in the quantum world, this power comes with subtlety, because the same openness that allows for many possibilities also makes the system delicate, sensitive to interaction, easily disturbed by its surroundings. And so, working with quantum information requires a kind of care, a quiet precision, almost like trying to listen to a faint melody in a noisy room. You must reduce the noise, preserve the harmony, protect the system from unwanted influence. Only then can the full richness of its behaviour be revealed. There is something almost poetic in this, that the most powerful forms of information we have discovered are also the most fragile, that to access deeper layers of reality, we must approach them gently, with patience, with attention, and perhaps with a certain respect for their subtle nature. As you sit with this idea, it may begin to feel less like a technical concept, and more like a shift in perspective, a move away from rigid, binary thinking towards something more fluid, more interconnected, more reflective of the underlying patterns we've been uncovering all along. Because from the structure of a snowflake, to the behaviour of light, to the connection between distant particles, a theme has been quietly unfolding, that reality is not built from isolated pieces, but from relationships, from possibilities that overlap, combine, and give rise to something new. And as we continue, we will begin to explore just how vast this space of possibilities can become, how quickly it expands, how richly it grows, and how it begins to stretch beyond anything we can easily imagine. As you rest with that image, a system that does not simply choose one path, but holds many possibilities at once, it begins to feel as though the quantum world is not just different, it is larger. Not larger in size, but larger in what it can contain. Because when we speak about information in the classical world, we are always dealing with limits that feel familiar. A system can be in one state or another. A sequence of bits can represent many patterns, but always in a way that unfolds step by step, one configuration at a time. You might imagine it like reading a book. Each page follows the last. Each sentence appears in order. The story progresses, but only along a single line. Even when there are many possible endings, you experience them one at a time. But in the quantum world, something much richer begins to unfold. Because when multiple qubits come together, their combined possibilities do not simply add up. They expand rapidly, gently at first, and then with increasing depth. Two qubits can represent more than just two separate pieces of information. They form a shared system where the possibilities are intertwined. 3 qubits, even more. 4, more still. And as the number grows, the space of possibilities begins to stretch far beyond what we can easily picture. It is not necessary to follow the exact numbers. In fact, it may be more helpful not to. Because the important point is not the calculation, but the feeling that with each additional element, the landscape of what is possible becomes vastly richer. You might imagine it like a forest. With just a few trees, the structure is simple. You can see through it easily. But as more trees appear, paths begin to branch, shadows overlap, new patterns emerge, and soon the forest becomes something you cannot fully grasp at once. Not because it is chaotic, but because it is deep, layered, full of subtle structure. In the same way, a quantum system with many parts does not just become more complex in a linear sense. It becomes more expressive, more capable of holding intricate relationships, delicate correlations, patterns that are not easily reduced to simpler pieces. And this is where the idea of quantum computing becomes especially intriguing. Because rather than processing information step by step, moving from one state to another, a quantum system can explore this vast landscape in a more unified way. It does not try every possibility one after another. Instead, it allows them to coexist, to interact, to shape one another. And from that interaction, a result emerges. You might picture it like standing at the edge of a wide valley. In a classical approach, you might walk every path, one by one, carefully mapping the terrain. But in a quantum approach, it is as if a soft wave spreads across the entire valley at once, touching every hill, every curve, every hidden path, and then, as the wave settles, it reveals something about the shape of the whole, not by visiting each point individually, but by sensing the structure as a whole. This is not magic. It is not faster in the sense of rushing. It is simply a different way of engaging with possibility, a way that reflects the deeper nature of the quantum world. And yet, there is something humbling in this, because even as we begin to understand the potential of such systems, we also recognize their limits, not limits imposed by lack of imagination, but by the sheer scale of what they contain. The number of possible configurations in even a modest quantum system can become so vast that it exceeds anything we can easily compare it to. More possibilities than grains of sand on a beach, more than stars in the night sky, even more than the number of atoms that make up the observable universe. And still, this is not something abstract. It is something that can, in principle, be built, held within a physical system, a collection of particles, arranged carefully, interacting gently, preserving their delicate relationships. There is something quietly astonishing about that such vastness can be contained within something so small, that an object no larger than a room, or even smaller, could hold within it a space of possibilities greater than the entire visible cosmos. It reminds us that size in the quantum world is not always what it seems, that depth does not always correspond to scale, and that the richness of reality is not measured only in distance, but in possibility. As you sit with this idea, it may begin to feel less like a technical concept and more like a quiet expansion of perspective, a sense that beneath the surface of the familiar world, there exists a layer of extraordinary depth, a hidden vastness, not distant, but present, not overwhelming, but subtle. And as we continue, we will begin to explore the boundaries of this vastness, the limits beyond which even these rich systems cannot go, where the structure of reality itself begins to impose constraints, where there are scales so small, so fundamental, that they define what can be known and what must remain beyond reach. As that sense of vast possibility settles, as you begin to feel how deeply the quantum world can expand, there is a gentle shift waiting just ahead, a quiet turning point, because whenever something grows in richness, in depth, in possibility, a natural question follows. Does it go on forever, or is there a boundary, somewhere, beyond which we cannot go? It is a question that feels almost instinctive. If you could look closer and closer at something, zooming in step by step, would there always be more to see? Or would you eventually reach a point where the idea of smaller begins to lose its meaning? You might imagine holding a photograph. At first you can see the whole image clearly, then you move closer, noticing finer details, textures in the surface, subtle variations in colour. You zoom further still until the image begins to break into tiny dots, and beyond that, there is nothing more to reveal. Not because the image disappears, but because you have reached the smallest meaningful unit from which it is made. In a similar way, physicists have long wondered whether reality itself has such a limit, a smallest meaningful scale, not just the smallest thing we can measure, but the smallest thing that can meaningfully exist. And as our understanding deepened, a remarkable idea began to take shape, that there may be a scale so small that the usual concepts of space and distance begin to dissolve, a scale where the smooth fabric of reality becomes something else, not necessarily broken, but no longer continuous in the way we imagine. This idea is often associated with what we call the Planck scale, but rather than thinking of it as a number, it may be more helpful to think of it as a boundary, a threshold, a place where our familiar descriptions begin to lose their clarity. To approach this scale, you would need to look at distances far smaller than anything we can directly observe, smaller than atoms, smaller than the particles within atoms, smaller even than the structures that define those particles themselves, a depth so extreme that it almost slips beyond imagination, and yet it is not just small, it is fundamentally different, because at this scale, space may no longer behave like a smooth, continuous stage upon which events unfold. Instead, it may have a kind of subtle structure, a limit to how finely it can be divided, not like a solid object that breaks into pieces, but more like a resolution, a smallest meaningful distinction. Just as a digital image cannot be divided beyond its smallest pixel, reality itself may have a point beyond which zooming in no longer reveals anything new. You might imagine trying to measure the position of something with infinite precision, to pinpoint its location exactly, without any uncertainty. At larger scales, this feels straightforward, but as you move closer to this deepest level, something changes. The act of defining a position becomes less clear, less stable, because the concepts we use, distance, location, separation, begin to blur. It is as though space itself becomes soft, not empty, but no longer sharply defined. And in that softness, the idea of a precise point begins to fade. This is not something we encounter in everyday life. Our world feels solid, continuous, reliable, but that may be because we exist far above this fundamental scale, where the deeper structure is gently averaged out, like looking at the ocean from a distance. From afar, the surface appears smooth, calm, but if you were to move closer, much closer, you would begin to see the subtle motion beneath, waves within waves, patterns that only reveal themselves at a different scale. And yet, even this comparison is only a hint, because at the deepest level, the behavior of space may not resemble anything we're used to seeing. It may not be a surface at all. It may be something more abstract, more foundational, and perhaps as you rest with this idea, it does not need to feel overwhelming. It can feel quiet, like reaching the edge of something not by force, but by understanding. A gentle recognition that there are limits, not imposed from the outside, but built into the nature of reality itself. Limits that do not diminish the richness of the universe, but define it, give it shape, give it meaning, because without boundaries there would be no structure, no distinction, no form, and so, this smallest meaningful scale, whatever its exact nature may be, becomes a kind of foundation, not something we can fully describe, but something we can sense, a quiet edge to how far smaller can go. And as we continue, we will begin to explore what happens when we try to push beyond that edge, what it means to look deeper than reality allows, and how, in that attempt, we encounter something unexpected, not just a limit of measurement, but a limit of knowledge itself. As that idea gently settles, that there may be a smallest meaningful scale, a quiet edge beyond which the notion of smaller begins to fade, another question begins to rise, a natural one. If there is such a limit, could we ever reach it? Could we, with enough care, enough precision, enough patience, look deeper and deeper until we arrive at that boundary? At first, it feels like something we should be able to do. After all, throughout history, our ability to observe has steadily improved. We have built microscopes that reveal cells, instruments that uncover atoms, detectors that sense particles far smaller than anything visible to the eye, each step bringing us closer, each refinement sharpening our view. It feels like a journey without end, a steady descent into finer and finer detail. But in the quantum world, this journey is not quite so simple, because to observe something, to truly see it at a very small scale, we must interact with it. We must in some way touch it, not physically, as we might touch an object with our hands, but through energy, a probe, a signal. Often this means using light, or something like it. And here, a subtle trade-off begins to appear. To observe smaller details, we need to use probes that carry more energy. You might imagine it like trying to see fine details in a dark room. A soft, dim light reveals only the broad shapes. But if you want to see the smallest textures, the finest patterns, you need a brighter, more focused beam. In the same way, to explore very small distances, scientists use forms of light, or particles, that have very high energy. These allow for sharper resolution, finer detail, deeper insight. But as the energy increases, something unexpected begins to happen. The act of observation becomes more intrusive, more disruptive. Imagine trying to observe the surface of a still pond. If you shine a gentle light, you can see the reflection clearly. But if you drop something into the water, even a small object, the surface ripples. The act of interaction changes what you're trying to observe. Now imagine that instead of a small disturbance, you introduce something far more energetic, a splash, a strong impact. The surface no longer simply reveals itself, it transforms, it reacts. At the smallest scales of reality, something similar occurs. To probe extremely tiny distances, the energy required becomes so large that it begins to affect the very structure of space itself, not just the particle you're observing, but the surrounding fabric of reality. And if you continue this process, increasing the energy further and further, there comes a point where the concentration of energy in such a small region becomes extraordinary, so intense that it begins to curve space around it, to such a degree that a kind of boundary forms, a region from which even light cannot escape. In other words, a black hole, not the vast distant kind that sits at the centre of galaxies, but a tiny fleeting one, formed not from collapsing stars, but from the sheer intensity of the observation itself. And in that moment, something profound happens. You are no longer able to see what lies within. The very act of trying to observe more deeply has created a barrier, a limit. Not because your tools are insufficient, but because the laws of nature themselves prevent you from going further. It is a quiet and humbling realization that there are boundaries not imposed by our ignorance, but by the structure of reality itself. You might imagine it like trying to listen to the faintest whisper in a room. At first, you lean in, reducing the noise around you, but if you try to amplify the sound too much, the system begins to distort. Feedback appears. Clarity is lost. There is a point beyond which the signal cannot be made clearer, because the act of amplification changes the signal itself. In the same way, when we attempt to observe the smallest possible scales, we reach a point where the distinction between observer and observed begins to dissolve. The two become intertwined, and the result is not a clearer picture, but a fundamental limit, a horizon of knowledge. This does not mean that reality disappears at that boundary. It does not mean that nothing exists beyond it. Rather, it suggests that our ability to describe, to measure, to define, has reached its edge, that there are aspects of the universe that remain, in some sense, hidden, not because they are distant, but because they are too deeply embedded in the structure of reality itself. And perhaps, as you rest with this idea, it carries a certain calm, a sense that not everything needs to be uncovered. That mystery is not a flaw in our understanding, but a natural part of it, a reminder that the universe is not only something we explore, but something that in quiet ways resists complete understanding. And in that resistance there is a kind of balance, a harmony between what can be known and what remains just beyond reach. As we continue, we'll take one more step into this idea of limits, not just in how we observe, but in how we imagine space itself, exploring the possibility that reality may have a kind of resolution, a smallest unit of structure, like the gentle grid beneath an image, a pattern that defines how finely the universe can be drawn. As that idea gently settles, that there are limits not only to what we can see, but to how deeply we can know, another possibility begins to emerge, a quiet, almost surprising one. What if reality itself has a kind of resolution, not just a limit to our observation, but a limit built into the structure of space itself? You might begin with something familiar, a photograph on a screen. From a distance it appears smooth, continuous, every colour blending softly into the next. But as you move closer, as you look more carefully, you begin to notice something subtle. The image is not truly continuous. It is made of tiny points, pixels, each one holding a small piece of information, a colour, a brightness, contributing to the larger picture. And beyond those pixels, there is nothing more to resolve, no finer detail hiding beneath, not because the image is incomplete, but because that is how it is built. Now, Imagine extending that idea, not to a photograph, but to the fabric of reality itself. It is a bold thought, and yet one that has quietly emerged from the study of physics, that space, the very stage upon which everything exists, may not be infinitely smooth. It may have a smallest unit of structure, not something we can easily point to, not a tile or a block in the usual sense, but a limit to how finely it can be meaningfully divided, a kind of underlying grain, subtle, invisible at our scale, but present. You might imagine it like a painting. From a distance, the brush strokes blend into a seamless scene, but up close, you begin to see the texture, the individual strokes that give the image its form. And yet, if you try to go further still, beyond the smallest stroke, the concept itself begins to lose meaning. There is no finer brush stroke beneath it, only the structure that is already there. In a similar way, if space has a fundamental resolution, then there is a limit to how precisely positions can be defined, not because we lack the tools, but because the concept of a more precise location may no longer apply. This idea becomes even more intriguing when we consider what happens in the presence of extreme conditions. Near black holes, for example, something remarkable occurs. The information that describes what falls into a black hole does not seem to disappear. Instead, it appears to be encoded in a way that relates to the surface of the black hole itself, not its volume, not its interior, but its boundary, as if the information about what lies within is somehow stored on the edge. This has led to a profound and subtle insight that the amount of information that can exist within a region of space may be limited, not by its size in the usual sense, but by the area of its boundary. It is a quiet shift in perspective, one that suggests that reality may be more like a carefully drawn image, where the total amount of detail is finite, rather than endlessly divisible. You do not need to follow the technical details to feel the significance of this. It is enough to sense the implication that the universe may not be infinitely detailed, that there is a kind of grain to reality, a smallest unit of structure, beyond which the idea of finer detail simply does not apply. And if this is true, it changes something subtle in how we imagine the world. It means that space is not just an empty backdrop, but something with its own character, its own limits, its own quiet structure. And perhaps, as you sit with this idea, it begins to feel less like a restriction and more like a kind of harmony, because limits give rise to form, just as a finite number of notes allows for music. A finite resolution allows for structure, for patterns, for the emergence of the world we experience. Without limits, there would be no distinction, no shapes, no recognizable forms. And so, the idea that the universe has a resolution does not diminish its richness. It defines it. It gives it texture. It allows complexity to arise within a framework that is both subtle and complete. You might return for a moment to the image of the photograph. From afar it is smooth, from up close it reveals its structure, and yet at every scale it remains meaningful. In the same way, reality can appear continuous, while still resting upon a deeper, discrete foundation, a quiet balance between smoothness and structure, between the infinite and the finite. And as we move forward, this idea will begin to connect with something even larger, because the same principles that govern the smallest scales also shape the behavior of the largest structures in the universe, from the fabric of space itself to the life cycle of stars. And in that connection, we will begin to see how the quantum world, subtle and hidden though it may be, reaches far beyond the smallest distances, quietly shaping the cosmos. As that sense of structure lingers, that reality may have a smallest meaningful scale, a quiet resolution beneath its surface. It becomes natural to wonder where these ideas lead, not just inward, toward the smallest distances, but outward, toward the vastness of the cosmos, because the same principles that shape the tiniest particles do not remain confined to that hidden world. They extend, they accumulate, and in doing so they begin to influence things of extraordinary size, entire stars. You might begin by imagining a star not as a distant point of light, but as something closer, a vast sphere of glowing gas, gently suspended in space. At every moment there is a quiet tension within it. Gravity pulls inward, drawing all of its matter toward the centre, a steady, persistent pressure, like a soft but constant hand. And yet, the star does not collapse. It holds itself up. In ordinary stars like our Sun, this balance comes from energy released by nuclear processes deep within the core. Heat pushes outward, countering the pull of gravity. But there are stars, older ones, quieter ones, where that source of energy fades, where the outward pressure of heat is no longer enough, and still, they do not immediately collapse. Something else takes over, something far more subtle. To understand it, it helps to return once more to the quantum world, to the behaviour of particles when they are brought very close together. Imagine a crowded room. At first, there is space to move. People can shift, adjust, find their place. But as more and more individuals enter, the room becomes tighter. Movement becomes restricted. Eventually, it becomes difficult to move at all. Now imagine that there is a rule, a quiet, invisible rule, that says no two people can occupy exactly the same position. Not even for a moment. Each person must maintain their own distinct place. Even if that place becomes very small, very constrained, it must remain separate. In the quantum world, a similar rule exists for certain particles. It is known as the Pauli exclusion principle. But rather than focusing on the name, it may be easier to feel its effect. Particles like electrons resist being compressed into the same state. They cannot all settle into a single identical arrangement, and as a result, when they are pushed closer together, they push back. Not through contact, not through force in the usual sense, but through the structure of their allowed states. This creates a kind of pressure, a quiet resistance, often called quantum pressure, or more specifically, electron degeneracy pressure. It does not come from heat. It does not rely on motion in the usual sense. It arises simply from the fact that the particles cannot all be in the same place, doing the same thing. And in certain stars, this pressure becomes the final support against gravity. You might imagine the star as slowly contracting, its matter drawn inward over time. As it becomes denser, the electrons are forced closer together. Their available space in terms of allowed states becomes more limited, and so their resistance grows, soft at first, but increasing steadily, until eventually it balances the inward pull. The star settles into a new kind of stability, not held up by heat, but by the quiet rules of quantum mechanics. These objects are known as white dwarfs. They are the remnants of stars like our Sun, compact, dense, and quietly enduring. There is something deeply beautiful in this, that the same principles governing the smallest particles, the ones we cannot see directly, are also responsible for holding up entire stars. That something as subtle as the inability of electrons to share the same state can counteract the immense pull of gravity across a mass larger than planets. It is a reminder that scale in the universe is not always what it seems, that the smallest rules can have the largest consequences, and yet even this balance has its limits, because as the star becomes more massive, as gravity presses inward with greater force, The quantum pressure must increase to match it. The electrons are pushed into ever tighter configurations. Their resistance grows, but only up to a point, and beyond that point, something changes. The balance cannot be maintained. But that is a story that unfolds slowly. For now, it is enough to rest with the idea that the universe is held together not only by grand forces, but by quiet constraints, that the same rules that shape the behavior of particles in a laboratory also shape the fate of stars. And perhaps, as you let this thought settle, it carries a certain calm, a sense that beneath the vastness of the cosmos, there is a kind of consistency, a gentle order, where the smallest details and the largest structures are woven together by the same underlying patterns. And as we continue, we will follow this thread a little further, to the point where even this quantum support reaches its limit, and where the quiet balance between gravity and resistance gives way to something new, greater than, as that quiet balance settles in your mind. A star held up not by fire, but by the gentle resistance of its smallest particles. Another question begins to form, a natural one. If this quantum pressure can hold up a star, can it hold up any star? Or is there a point where even this subtle support is no longer enough? You might return for a moment to the image of a crowded room, people standing shoulder to shoulder, each maintaining their own small space. At first, the room can accommodate more and more individuals. The pressure builds, but it remains manageable. Everyone adjusts, compresses slightly, finds a way to fit. But there comes a moment when the room simply cannot hold any more. No matter how much people try to move, there is no space left to rearrange. The structure reaches its limit, and beyond that point, something has to change. In a similar way, the quantum pressure within a star can only resist gravity up to a certain threshold. As the mass of the star increases, gravity becomes stronger, pulling inward with greater intensity. The electrons, already tightly packed, are forced into even more constrained states. Their resistance grows, but not without bound. There is a limit, a quiet boundary written into the laws of physics. If the star remains below this limit, the balance holds. The star becomes a white dwarf, stable, compact, quietly glowing as it slowly cools over time. But if the star's mass exceeds this threshold, the balance cannot be maintained. The quantum pressure of the electrons is no longer enough. Gravity continues to press inward, and the structure begins to collapse. This threshold is known as the Chandrasekhar limit. But rather than thinking of it as a specific number, it may be more helpful to see it as a natural boundary, a dividing line between stability and transformation, a point where the rules governing the system begin to shift. Below it, one kind of structure is possible. Above it, something new must emerge, and what follows is not abrupt, but inevitable. As the collapse continues, the electrons are pushed closer and closer together. Eventually, they are forced into such extreme conditions that they can no longer remain as they were. The distinctions that once defined them begin to blur, and under these intense pressures, the matter itself changes form. Protons and electrons combine, forming new particles, a different state of matter, denser, more compact. The star transforms, not gently, but through a profound shift in its internal structure. And while the details of this transformation can become complex, the underlying idea remains simple. There are limits, not imposed from the outside, arising naturally from the interplay of forces, gravity pulling inward, quantum rules pushing outward, and between them, a balance that holds until it cannot. There is something quietly elegant about this, that even in the vastness of the cosmos, there are boundaries, points where one kind of behavior gives way to another. where stability transitions into change, and it all begins not with something large or dramatic, but with the properties of the smallest particles, the way electrons arrange themselves, the way they resist being compressed, the rules that govern their existence, these microscopic details, written into the fabric of quantum mechanics, determine the fate of entire stars. You might pause here and let that connection settle, that something as subtle as a rule about particle states can shape the life and death of objects larger than planets, that the universe, in its vastness, is guided by principles that operate quietly at every scale, from the smallest to the largest. And perhaps, as you reflect on this, it brings a sense of continuity, a feeling that the universe is not divided into separate layers, but woven together, that the quantum world is not hidden away, but present in everything, even in the stars above, even in the processes that unfold across millions or billions of years. There is no separation, only a seamless extension of the same underlying rules. And yet, this is not the end of the story, because beyond these transformations, beyond the limits of stars and the pressures that shape them, there lies an even broader horizon, one that extends beyond individual objects, into the structure of entire systems, into the future of exploration, into the way life itself begins to interact with the cosmos. And as we continue, we will take a step outward, from the quiet collapse of stars to the gentle expansion of a civilization beginning to reach beyond its home. As that image fades gently, a star reaching its limit, its fate shaped by the quiet rules of the smallest particles, there is a soft widening of perspective, a shift from what happens out there to what is beginning to happen here. Because the same universe that forms stars also forms life, and in at least one small corner of that universe, life has begun to notice, to observe, to understand, and slowly to move. You might imagine standing on the surface of the earth at night, looking upward, the sky filled with distant lights, each one a star shaped by the same forces we have just explored. For most of human history, those lights remained far beyond reach, points of wonder, objects of curiosity, but not destinations. And yet, in a very short span of time, something changed. Humanity began to step beyond the surface of its home, first in small ways, short journeys, careful experiments, then gradually, with increasing confidence. And at the heart of this change was a simple idea. That reaching space did not have to be a one-time event, that it could become something repeatable, something sustained. You might think of it like learning to travel across an ocean. At first, each journey is rare, uncertain, difficult. But over time, as knowledge grows, as tools improve, those journeys become more familiar, more reliable. Eventually, they become part of the structure of everyday life. In recent years, something similar has begun to take shape with space. The development of reusable rockets, systems that can return, land, and be used again, has quietly changed the nature of space travel. Instead of building a new vehicle for each journey, we are learning to reuse what we have, to refine it, to make it part of an ongoing process. And this has a subtle but profound effect, because it lowers the barrier. It makes access to space less rare, less distant, more continuous. You might imagine it like a path forming where there was once only open terrain. At first, each step is difficult, uncertain, but as more journeys are made, a trail begins to appear, a route that can be followed again and again, and eventually, that trail becomes something more, a connection, a kind of invisible roadway, circling the Earth, Orbit, a region that is no longer entirely separate from our world, but not fully part of it either. A threshold space. And within this space, new possibilities begin to emerge. Satellites that observe the Earth, quietly gathering information about weather, climate, movement. Instruments that study the cosmos, looking deeper into the structure of the universe. Platforms that support communication, connecting distant parts of the planet. All of this forming a kind of early infrastructure, not built of roads or buildings, but of pathways and connections, of objects moving in careful, continuous motion around the Earth. There is something gentle about this expansion. It is not a sudden leap, not a dramatic departure, but a gradual extension, a reaching outward, step by step. And perhaps as you consider this, it begins to feel like a natural continuation of the story we have been exploring, from particles and to atoms, to stars, as to planets, to life, and now, from life to movement beyond its origin. Not as an escape, but as an extension, a way of engaging more deeply with the universe that gave rise to it. And yet, even as this expansion begins, it remains delicate, careful. Like the quantum systems we explored earlier, it requires balance, precision, attention. Because space is not an easy environment. It is vast, harsh, unforgiving in many ways, and so each step outward must be taken with care, with an understanding of the limits and the possibilities. There is no rush, no need for urgency, only a quiet progression, a sense that this is something unfolding over time, and perhaps, as you let this idea settle, it carries a certain calm. That humanity's movement into space is not a sudden transformation, but a gradual unfolding, a continuation of the same curiosity that led us to study snowflakes, to explore light, to understand the behavior of particles, now extended into the cosmos itself. And as we continue, we will begin to look further outward, beyond orbit, beyond the immediate surroundings of Earth, toward a future where the resources of space, the materials drifting quietly between planets, may become part of this unfolding story. Not as something to conquer, but as something to understand, and perhaps gently make use of. As that gentle image settles, pathways forming around the Earth, a quiet network of motion circling just above the atmosphere, it becomes easier to imagine taking one step further, not a leap, just a continuation, a soft widening of the horizon, because once a path exists, it invites movement, and once movement becomes possible, it invites exploration. You might picture drifting beyond the thin shell of orbit, moving slowly outward, past the familiar blue curve of Earth, into the darker expanse where distances begin to stretch. At first, there is still a sense of connection. The Earth remains visible behind you, a steady reference point. But as you move further, something changes. The space between objects begins to feel larger, quieter, more open. And within that quiet, there is something else. Not emptiness, but presence. Because scattered throughout this vast region are countless objects, fragments of rock and metal, some small, no larger than a stone, others immense, stretching across many kilometers, asteroids, remnants from the early formation of the solar system, pieces that never became planets, but continue to orbit the sun in slow, patient paths. At first glance, they may seem insignificant, distant, irrelevant to everyday life. But if you look more closely, a different picture begins to emerge. These objects are not random. They're composed of the same materials that make up planets, and even the Earth itself. Metals, minerals, elements that, on our world, are often difficult to access, hidden deep beneath layers of rock. Here in space they exist in abundance, exposed, waiting. You might imagine it like walking through a quiet landscape where resources are scattered gently across the terrain, not concentrated in one place, but spread out, requiring patience, movement, and care to reach. And for the first time in human history, it is becoming possible to consider interacting with these materials, not in a hurried or forceful way, but gradually, thoughtfully, with the same sense of exploration that has guided science for centuries. This idea is sometimes described as a space economy, but rather than thinking of it in terms of trade or industry, it may be more helpful to imagine it as an extension of presence, a way of being in more than one place, of engaging with the broader environment of the solar system, because the resources of space are not limited in the same way as those on a single planet. They are vast, distributed, and in many ways more accessible once the initial pathways have been established. There is something quietly transformative in this, because for most of human history, survival and growth have been shaped by the limits of Earth, by the availability of land, of energy, of materials. These limits have guided decisions, influenced civilizations, shaped the course of history. But as we begin to move beyond the surface of our planet, those constraints begin to shift, not disappear, but change. The boundaries expand, and with that expansion comes a new kind of possibility. Not unlimited in an absolute sense, but far broader than what came before. You might think of it like living in a single room, and then slowly discovering that there are doors. At first, you remain where you are. Then you open one door and find another space, then another, each new space offering something different, something that was not available before. And over time, the idea of where you can go begins to change. It becomes less fixed, more open, and yet, as with everything we have explored, this expansion is not something to rush. It unfolds gradually, carefully, because the same principles that govern the smallest particles and the largest stars also apply here. Balance, constraint, interaction, the need to understand before acting, to observe before altering. There is no need for urgency, only a quiet awareness that the universe is not closed to us, that it offers possibilities, not as something to be taken, but as something to be engaged with, gently, thoughtfully. And perhaps, as you rest with this idea, it brings a sense of perspective, that the story of humanity is not confined to a single place, that it may extend, slowly and naturally, into the wider structure of the cosmos, not as something separate from it, but as part of it, a continuation of the same patterns we've been following all along, from particles to atoms to stars to life, and now to movement beyond. And as we move toward the final part of this journey, there is one more question waiting quietly beneath the surface. A question not about where we can go or what we can reach, but about what it means that we are here at all, that in a universe shaped by quantum rules, structured by limits, and filled with vast possibility, there exists something that can observe it, reflect on it, and perhaps understand it. As that quiet sense of expansion lingers, pathways extending beyond Earth, possibilities unfolding gently into the wider solar system, there is one final step in this journey, a step that does not move outward, but inward, back towards something more familiar, more immediate, back toward you. Because after travelling through patterns in snowflakes, through the strange behaviour of light, through the subtle rules of quantum mechanics, and the vast structures of stars and space, a question remains, a quiet one. What does all of this mean for us? You might begin by considering how small we are, in physical terms, A single human life, measured against the scale of the Earth, is already modest. Measured against the Sun, smaller still, against the galaxy, almost unnoticeable, and against the observable universe, so vast that even imagining the comparison becomes difficult. We are, in a very real sense, nearly invisible. It is easy in moments like this to feel insignificant, to imagine that our presence does not matter, that we are simply a small and temporary feature in a universe that continues on without us. But there is another way to look at it, a quieter, more subtle perspective. Because while we may be small in size, we are not small in function. Within you, right now, is a system capable of something remarkable. You are aware, not just present, but conscious. You can reflect, you can observe, you can ask questions about the very universe that gave rise to you, and that, in itself, is something extraordinary. Because for most of the universe's history, there was no one to notice it, no one to observe the stars forming, no one to wonder about the nature of light, no one to ask why reality behaves the way it does. For billions of years, the universe unfolded quietly, structures formed, particles interacted, stars ignited and faded, all without observation, all without reflection, and then, gradually, through a long chain of events, something changed. Life emerged, not immediately complex, not immediately aware, but slowly, over time, increasing in its ability to respond, to adapt, to sense its environment, and eventually to think, to form models of the world, to develop language, to create tools, to look outward and inward. And at some point along that path, the universe became capable of examining itself, through you, through others like you, through every mind that has ever paused to look at the night sky and wonder. There is something deeply meaningful in that, not in a dramatic or overwhelming way, but in a quiet, steady sense, that the same universe governed by quantum rules, structured by limits, and filled with vast possibility, also contains within it the ability to become aware, to reflect, to ask questions. You might imagine it like a vast ocean. For most of its existence, the ocean simply moves. Waves rise and fall, currents shift, patterns emerge and dissolve, and then, in one small region, a ripple forms that can notice the ocean, a pattern within the water, becoming aware of the water itself, not separate from it, but part of it, and yet capable of seeing it in a new way. That is what consciousness may be, not something outside the universe, but something that arises within it, a way for the universe to experience itself, to observe its own structure, its own patterns, its own unfolding story. And perhaps, as you sit with this idea, it begins to soften the sense of distance we often feel between ourselves and the cosmos, because we are not separate from it. We are made of the same particles, the same atoms, forged in the same processes that shape stars, the elements in your body, the oxygen you breathe, the carbon that forms your cells, all of it, once part of something larger, something ancient, something that existed long before life began, and now, arranged in a particular way, it forms you, a temporary structure, yes, but one capable of awareness, and that awareness in itself may be rare. We do not yet know how common life is in the universe. We have found hints, possibilities, environments where it might exist, but so far, we have only one confirmed example, here, on this planet. And while it is entirely possible that life exists elsewhere, it is also possible that it is not widespread, that it arises only under certain conditions, through a delicate balance of factors. If that is true, then consciousness may be something quite special, not in a way that separates us from the universe, but in a way that highlights our role within it. Because if awareness is rare, then each instance of it carries a certain weight, a certain significance, not imposed from the outside, but emerging naturally from the structure of reality itself. And as humanity continues to grow, to learn, to explore, that role may begin to expand, not suddenly, not dramatically, but gradually. As we extend our presence beyond Earth, as we interact with the wider environment of space, as we develop new ways of understanding and shaping the world around us, we become participants in the unfolding story of the universe, not just observers, but contributors, in small ways at first, and perhaps, over time, in larger ones. There are ideas, still speculative, still uncertain, that suggest life could one day influence processes on a much larger scale. That intelligent systems might interact with the cosmos in ways we do not yet fully understand, not through force, but through information, through structure, through the ability to recognize patterns and gently shape outcomes. These ideas are not established facts, they are possibilities, but even as possibilities, they point towards something meaningful, that the story of the universe is not fixed, that it continues to unfold, and that within that unfolding, there is room for awareness, for participation, for quiet influence. You might return for a moment to where we began, a snowflake falling gently, shaped by invisible rules, a beam of light revealing the structure of energy, a particle exploring many paths at once, each of these moments small in themselves, but connected, part of a larger pattern. And now, here you are, aware of it, thinking about it, letting these ideas move softly through your mind. And perhaps that is enough, not a conclusion, not a final answer, but a gentle recognition that you are part of this story, not separate from it, but within it. A brief moment of awareness in a universe that has been unfolding for billions of years and may continue for billions more. And in that moment, there is a kind of quiet beauty, not loud, not overwhelming, but steady, present, like the soft hum of something vast, continuing just beyond the edge of thought. And so, as we reach the end of tonight's exploration, you might simply let that feeling remain. No need to hold on to it tightly, no need to resolve it completely, just allow it to rest, gently, in the background, a quiet reminder that beneath everything familiar, there is a deeper layer, and within that layer, a place for wonder. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could. Use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully wherever and whenever you may be.